One. Hello, I'm Romulus Khalil, and this is my Lab 3 on black hole and orbits. Here's a brief overview. So part one, the purpose of this part is to observe the motion of a star around a black hole and to use this motion to predict the mass of the black hole. The purpose of this part, for part two, is to simulate the motion of a body in space around a planet and to see if we can force said ship into a figure-8 orbit. And those are the fundamental physics principles that are applied. Newton's second law is the force of an object is equal to its mass times its acceleration. More massive objects require more force to move. And gravitational force is the gravitational force of a mass m1 and mass m2 separated by r distance. Here's the different formulas: position update, velocity update, average velocity. So here's part one, the experiment. We had our system, the black hole, and our surroundings, a star. Our predicted positions and mass were calculated using computational models in GlowScript. For part two, much the same, but this time it's the spaceship and the moon as our system, and our surroundings are the planet and the black hole. Our predicted positions, once again, were calculated in GlowScript. Is the initial conditions for part one, a star mass of 2.0 E30. And for part two, here's our initial conditions. That's ship speed x, ship speed y, and our initial velocity is just those put in their respective x and y components. So here's the GlowScript for part one. That's the gravity force. That's the initial mass I was talking about earlier. Delta T equals 0. And that's all the initialization I did. But right here, we do our V init, V final calculations, P init, P final calculations, and then we use that to get the mass of the black hole. And then for part two on the GlowScript, here's all of our initial conditions right here. And then we have moon speed, moon velocity, those were given to us. And then we do all these calculations with the position update formula and the velocity update formula to find all these FNet values. And then we can update the moon velocity and the ship velocity. So here's the output for part one. As you can see, we found an average black hole mass of that. We'll go into more detail on that later. And here is part two's output. There's the moon's, there's the orbit that we were able to find by guessing and checking the different velocity values. So results of part one, average black hole mass is that value right there, and the initial velocity after all of our guessing and checking, this was also part of my initial conditions, is negative 2.5 E4340. Discussion, possible errors. So possible error was poor guessing. I did just guess and check for the initial velocity on part two. Who's to say I didn't guess and check incorrectly? And here's our discussion questions. So part one, how is the net force in its parallel/perpendicular components different from the rate of change of momentum in its components? They're the same mathematically, but the rate of change of momentum is easier to find than the net force because we just need to know the system's change in velocity and motion rather than knowing all the forces acting on a system. And for part two, what if the system had a black hole, star, planet, and moon? The dominant force would come from the black hole, but the planet and moon would have some effect. Conclusion, for part one, we can accurately predict the mass of an object by observing its motion and the motion of the objects around it. And for part two, the same can be said for velocity. We can predict the initial velocity of an object by observing its motion. And that is it.